there's two things I definitely want to do today that I feel kind of will round out everything we've done in complexity theory. And then there's a whole bunch of things that we could do today and the next few days. So one of them is something that Neil asked about the other day, and I just want to get a sense who might think that's cool. He asked about something called the recursion theorem, which, as far as a neat idea goes, it's a really neat idea. And as far as an application goes, it's typically explained to students in the sense of, go home and write a program that does nothing but output itself. Okay, so you run the program, and its output is the program. And this is not as easy as it seems at first, because when you try to output the program itself, you feel like you're doing this self-referential infinite loop, and you get stuck, and you can easily convince yourself that, oh, there's no way to do this, and it's probably some reason similar to the diagonalization stuff, and I better stop trying. But it turns out that there is enough leverage to self-reference yourself in a program to print yourself out. And that's what the recursion theorem says. It says you can build a Turing machine whose output is the description of the Turing machine itself. That's more or less what it says. It says a little more than that. So anyway, I might be able to do that tomorrow. Does that sound like something fun you want to see? Yeah? All right, we can do that. It's a little theoretical, but what I did this morning is I went on the web, and I figured, you know, somebody's got to be given this assignment in 200 different classes all over the country, and they do. And I found a solution in C, and C++, and Java, and I can just give those to you if you want to see what they look like. But the idea of the solution is really kind of a 6 or 7 line description of what you want to do. And then the details of how to do it differ from language to language to language. And the esoteric minutia is actually not trivial, and it's good to have a real solution along with the idea that's behind it. So I'll try to do that tomorrow. I want to do it on a scratch day when everybody's really clear, and it might be a good way to kind of end off the whole month, which is all about these very strange constructions. All right, so today there's two main things I want to do. One is this thing called Savitch's theorem, and one is something called space hierarchy. There's that bullseye again. Half a bullseye.
Savitch does ellipses so we can write horizontally.
Savitch's got an editor. This is deterministic logarithm space. That's non-deterministic logarithm space. Remember, when you talk about space that's less than the input size, it means that the input's on its own little tape over here, and the space you're measuring is the extra space you need. So that's the log space, polynomial time, non-deterministic polynomial time, polynomial space, deterministic, and then exponential time, deterministic. So the question that came up yesterday is, how come there's no non-deterministic polynomial space? And my answer was that it's the same as this, that these two classes are the same. And the reason they're the same is because, unlike time, where you have to pay a lot to turn non-determinism into determinism, with space, you don't pay too much. Okay, space is cheaper as far as non-determinism goes. So if you want to go from a non-deterministic time algorithm to a deterministic time algorithm, you tend to have to pay an exponential amount. If this thing runs in time n, then this will run in 2 to the n. And if this runs in time n squared, this runs in 2 to the n, well, 2 to the n squared, more or less, or 2 to the n times n squared. But some exponential growth going from non-determinism to determinism. And nobody knows if you can do better. That's a fundamental question in complexity theory. With a lot of practical applications, if anybody found out any way to do better. We don't think there is a way to do better. But here, with space, you can actually pay a small price to go from non-determinism to determinism. And here's the theorem. The theorem says, if you use S of n space in a non-deterministic Turing machine, S of n space in a non-deterministic Turing machine, you can do the same thing with the square of that space in a deterministic Turing machine. So you don't pay an exponential blow-up, you pay a square blow-up. Therefore, if somebody gives you a non-deterministic algorithm that runs in polynomial space, like n to the fourth, then you can run it deterministically using n to the eighth space, squaring that n to the fourth. And that's why any polynomial space algorithm ends up being, that's a non-deterministic one, ends up being a polynomial space algorithm that's deterministic, because squaring something doesn't change it from being a polynomial to not being a polynomial. Now let's go down here to these log space ones. Here we have deterministic log n space, and this is non-deterministic log n space. So according to this theorem, what could I put over here around non-deterministic log space? That's D. What deterministic amount of space? This is log n, so this would be D log squared n. Okay, I could square that space and do it deterministically. Everybody see that? So these are not classes of like whole polynomials. These are just a particular function log n, and I can make this little kind of containment. It's not exactly the same. DL is not the same as D log squared as far as we know, but it goes in this order. Okay. If I said like polylog, you know, any log exponentiation, log to the third, log to the fourth, log to the fifth, then D polylog is the same as N polylog, for the same reason as these two are the same. All right, that's a big picture. Are there questions so far? So I want to explain this today and why this is true. The next thing relates to the same idea. One of the few containments that we can actually show is proper in this diagram, that we can actually separate and say there really is something out here that isn't in here. One of the few things is what are called hierarchy theorems. That if you give me an algorithm that runs in linear time, I can find you a problem that will not be solved by any algorithm in linear time, that will need, say, space, that will need n squared space. And if you try hard enough, you can find another problem that's going to need n cubed space and n to the fourth space. So, for example, DL and D log squared, those separate by a log L, by a log n. Those might become separated in the hierarchy theorem. But certainly, DL and P space will become separated. There's enough of a jump between log L and polynomial space that I can prove to you that there are things out here that are not in here. So it separates our classes legitimately a little bit. That's what a hierarchy theorem does. And there's one for time also. Okay? There's details about just how much of a push up you have to get before you get a new hierarchy. Like, is it certainly if you multiply the complexity by n, that's enough. Actually, if you multiply it by n to the anything, it's enough. But multiplying by log n, well, there's some issues there. For time, there's a similar hierarchy theorem. Intuitively, again, if you multiply by a factor of n, it's enough to get a new complexity class. So there are problems in n squared that can't be done in n, problems in n cubed that can't be done in n squared, etc., all the way through a real hierarchy in this P area. So we're going to talk about a space hierarchy. The time hierarchy proof is very much the same, and the proof of space hierarchy is very much like diagonalization. It's just diagonalization thrown on a different kind of problem. And it's similar to one of the extra credit problems I gave you where you throw diagonalization on oracles. So this is diagonalization thrown on space hierarchy. So you'll see diagonalization again, and it'll prove that there are some problems that can't be done in a certain amount of space, and that can be repeated. So the next level and the next level and the next level, and there's a whole hierarchy of problems, one which can't be done with the space of the one below it. So I want to do those two things today. Then we'll talk a little bit maybe again about alternation. And then we'll see how much time we have left. And I'll leave maybe the self-referential stuff for tomorrow if we get around to it. OK, questions about this stuff? There's also some reductions I'd like to do, and maybe more NP-complete ones or P-space complete ones. I did a lot in algorithms, and I know you're probably tired of them, but you have some homework problems on them, and I think they're fundamentally important. So it might be useful to see some more examples of them. And I have another one today that I can do, and we'll see if we have time. I'll get to it. All right. Any questions? Ready? All right, so let's start with Savitch's theorem and work our way down. I can get rid of the non-determinism, and all I have to pay for it is s squared of n space. Right? Now, what I want to do here is try to simulate any non-deterministic machine that uses s of n space and not care so much about how much space I use. Let's just do any kind of simulation and see where we are, and then see if we can cut that down to get s squared of n. If our first attempt actually gets this, then it's not much of a hard theorem. We just simulate it, and it turns out we don't use so much. It doesn't end up being exponential like the other case. But I think our first attempt will end up being exponential, and we'll have to think about how to cut that down. And that'll give us some motivation about where to go. All right, so let's try. Somebody's got a non-deterministic machine, and it uses s of n space. How do you simulate it? What did we do when we simulated non-determinism for time? What did we do? What was the basic idea? Right, we had a tape that listed all the choices, and we tried all those choices. Now, rather than think of it in terms of the Turing machine, we think of it in terms of this tree of possibilities. Here's the non-deterministic machine. Here's the initial configuration of the Turing machine. Here are the choices. I'm going to just make 2 choices here at every step just to make it easier for us to do calculations. There could be more choices, but there's some fixed number of choices at every step. And this represents a tree of possible computations. And a particular one starts from the initial configuration and makes choices and goes down to some configuration at the bottom. And if this configuration says yes, then we accept. And if they all say no at the bottom, then we say, no, I don't accept. Okay, that's what a non-deterministic machine does. And we have to go ahead, given a description of how to get this tree. That's what the Turing machine really is, a description of how to build this tree, a description of how to write the configurations out, and what the choices are at each step. Now you have to write a program that's going to take this description of the tree and go ahead and figure out, is there a way to get from the start to the bottom? And you're given that this machine doesn't ever use more than s of n symbols on its tape, whatever good that is to help. Right? So let's first see if we can simulate this at all. Somebody gives you this Turing machine, they give you an input, you're trying to find out whether the Turing machine accepts the input, and you have a deterministic program in order to do it. So we'll do what Chris said a minute ago, we'll try all the possibilities. Right? But how far can this tree go down? It can go down pretty far. It can go and go and go. Right? So we can simulate it, and it doesn't seem to be any limit on the time we'll spend simulating this. All right, so maybe it'll go forever. But how much space is it going to use? Well, if we actually build this tree up, it's going to use an infinite amount of space too. So my first gut instinct simulation uses an infinite amount of space. I have now paid an infinite amount to move from s of n. And that's pretty bad. So let's do better. Let's get it down to a finite amount, and then let's get it down to s squared. Do I really have to go forever before I answer yes or no? It's something we talked about yesterday. It's very, very crucial. If you're given a machine that uses at most s of n space, then what do you know about the number of different configurations in that machine? The total number of different possible states that machine could conceivably be in. Remember, it's q k to the s of n times s of n. That's the different number of configurations. This is the number of states in the machine. This is the space it's using. This is the number of symbols on the alphabet. That's the space that it's using. These are all the number of states in the whole machine. If the machine ever enters one of these states twice, it's in some infinite loop. So if it ever enters one of these states twice and hasn't accepted something, you know you can stop and say it's never going to accept. So if that's true, how far down do you have to build this tree? Not infinitely down, just as many levels down as there are different configurations. There's no reason ever to go past the point where you would have a double configuration. If you're going to find an accepting computation, you'll find it before a double appears. A double is just going to loop you, send you back to here. So that's the first thing. The height of this tree that we'd have to actually generate is bounded by this number. So the height of the tree is less than or equal to that number. Okay, that's a big number. How many nodes are in a tree with this height? A binary tree with this height? 2 to that number. Well, that's hideous. I mean, this is exponential to the exponential. But now at least we've got a finite step, okay? Now we're closing in on Savitch's theorem. That's why the theorem has got a name, right? Because when you try to just do it on your own, you don't get the answer right away. So somebody finally figures out how to do it, and they get their name on the theorem. Once you understand Savitch's theorem, you're going to say, hey, I could have done that. And that'll be in about 10 minutes. All right, so we knocked it down from infinity to finite. I can take S of n space in a non-deterministic machine, and if I do the most brute force thing, which is just go ahead and build this whole tree and store it in my memory, and then look at it, line by line by line, that takes this much space. Exponential, exponential. Can we improve on that? Chris says yes. Who else says yes, we can improve on this? Is there any need to store the whole tree to figure out if you can get from here to an accepting one on the bottom? We don't have to build the whole tree. We can kind of build it as we go down, like a depth first search, up until that depth. If we hit an accepting computation, we stop and say yes. If not, we back up and shoot at another branch that goes down. At any time, what are we storing in memory? We're storing a path from the top to the bottom, but not all the other branches. We don't generate those in advance. We leave those ungenerated and just remember where we're up to and generate them as we back up in the depth first search. It's a classic depth first search where you're given the description of the tree, but you don't actually have to store the whole tree. You just build it up as you go, and when you come back, you build up another path of it. When you come back, you build up another path of it. It's like a traversal through a tree, and you only store the path that you're currently traversing. And the way you build the rest of the tree is that you look at the Turing machine, and it tells you how to build the rest of the tree when you need it. And you've done this, actually, in programs. This is not something that's abstract. You did it in the Go program in algorithms. You did it in what's the name of that game? That ball game in the Java program. You did it a number of times. You've done these depth first searches. So what does that do to our space? It takes it down from this and makes it into... It takes rid of that 2 to the something factor. Now it's just the length of this thing, which is q, k, s of n times s of n. Now, I actually am a little bit, just a teeniest bit careless in that this is assuming that I can store every one of these dots in one space. Right? This is the number of levels in my tree. The longest thing I have to store is a path from the top to the bottom. But actually, I can't just store a configuration in one cell or in a constant number of cells. How many cells does it take me to store one of these configurations? What's in one of these configurations? It's a picture of the tape, what the state is, and where the head is. How many cells does it take me to store that? S of n, because I know that the tape's never going to be more than S of n cells. So each one of these little dots takes S of n cells in order to represent it. No more than that. So I really need to multiply this by S of n. And I really should have done that here too, but we were so far off, I figured, why bother adding another factor? Now we're getting closer, so I want to give you the more realistic view. All right. So all we got to do is get rid of this part. Whoosh. That's not going to be so easy. All right, questions so far? Has anybody read Savitch's theorem, looked at it in the book yet? Yeah? Did you get it? Yeah? Most of it? Okay.
Carry on.
We will. We're going to carry on in just a minute. All right, any questions so far? Good, good, good? All right. I'm doing this slowly because I really think this is important. It's nice to see a counterpart to what what's the biggest open problem in time is just a theorem with a solution in space. And maybe one day someone will have a proof that the time exponentiation is required, and it'll just be so-and-so's theorem, and this was open for 200 years, but now it's an exercise in your homework. That's how things go. Okay, so let's go back to this picture. We have the potential to build this tree as deep as we want. We can make any piece of it we want at any time. We want to know if we can get from this configuration to an accepting configuration, any one, and we don't want to use as much space as actually generating a whole path. We don't ever want to hold a whole path from here to the bottom. That's way too much. Now, each configuration we store is going to take S of n symbols. So how many configurations can we conceivably store and still get away with this theorem? S of n. We got S of n for each configuration, and S of n configurations we have room to store. That gives us S squared n. S of n times S of n. So how can we go ahead, and go away from the abstraction of a Turing machine, just this picture. You can generate this picture as big as you want. I'm giving you the initial configuration. You got that. I'll give it a name. It's called I0, the initial configuration. Okay? And you get all the time you want. We're only measuring space here. So take all the time you want. Tell me, is there a way to get from I0 to any of the final configurations, which I'll number, I'll just give them names. We'll call them IF0, IF1. These are final configurations that accepting configurations. There might be, so they say there's 3 of them. Is there any way to get from here to here? You're given a description of exactly what configurations this can go to, description of how to build this tree. And I want to know, can I get from here to here? You have all the time in the world you want, but don't store too many things. So right now I've stored 4 things. That's not so bad. Maybe I shouldn't even store 4. Why don't I just do these one at a time? Now I've only stored 2 things. If I can't get from here to here, I'll try the next final configuration. I can use all the time I want, so why not just store as little as possible and then use the time to do it? So I'll take any final configuration, and I'm going to try to get from here to here. How do I do it? So just going through this tree and looking for a path from here to here is too much space. All right, so I'll give you a hint, which will give you the idea that Savitch came up with, and then we'll talk about his idea in detail, and I'll write down the little algorithm. But the hint is that trying to find out whether there's a path from the node that represents this configuration to the node that represents this configuration, when you're given a way to generate the next stages in the path, that's like a linear search. That's like I'm searching for something from here to here, and I'm going to look through the whole path and store it as I go. Right? So if you want to cut that down, what's the normal way to cut down linear search? Is to do like a binary search. But there needs to be some ordering to do a binary search. And we'll get to that in just a second. But let's say we did cut this down to a binary search. Let's see if that actually works, because then we have a goal. If we want to see whether we can get from here to here and we do it in a binary search, then first we store, say, something in between that's going to be halfway. That takes half the number of steps and then half the number of steps from there again to get to the end. We'll call that the middle configuration. So now I've got 3 things stored. What do I do next? What if I find a middle one here? Middle. And then maybe a middle one here and a middle one here. Sooner or later, these configurations are going to be 1 apart. Okay? How many configurations would I store until they became 1 apart if I just keep having this first interval? I have it, and sooner or later, I get an interval that's just 1 apart. If I had 64 to begin with, and I halved it all the time until I got something with 1, I would have 6 different stages, right? I'd have the log base 2 of this. But what did I really start with? What's the real distance between I0 and IF0? It's not 64. It's really this. So if I manage to do my search in a way that I only store half points, then I can cut it down to the log base 2 of this. And the log base 2 of this is going to be what? More or less. Say the k was a 2. It makes it easier. The log base 2 of this is going to be S of n times log of S of n, right? Not times. S of n plus log of S of n. Right? Because when you take logs of things and they're multiplied, they end up being added. And when you take logs of things and they're exponentiated, they end up getting multiplied. So S of n log 2 of k, which is a constant, plus log S of n. And that's S of n, more or less. So we'd have only S of n different configurations stored, and that's what we're hoping to do. So that's our goal. Our goal is to kind of do this in a binary search kind of a way. And it's not going to be so tough to do it. We just have to be a little imaginative. So let me stop for a second. We started out that here's the initial configuration, here's the final configuration we're hoping to get to, right, Gary? And how far are they apart in the worst case? They're this far apart. They're an exponential number of steps apart in S of n. So what I'm hoping to do is cut that exponentiation down to just S of n. And the way we're going to do it is hopefully find the middle part, find the next middle, find the next middle. And if we can figure out a path from here to here and only store middle parts, then we don't actually ever have to hold the whole path in memory at any time. What's a good way to explain this that isn't...
Can I make it S of n log S of n?
What's that?
And the binary search would convert one of your S of n orders into a log.
Yeah, take the log of this. That's what's happening. So you get the log of q, that's a constant. The log base 2 of k to the S of n, that's S of n times the log base 2 of k. So that's a constant times S of n. And then plus log base 2 of S of n. So the overwhelming factor there is the S of n factor. So that's how many configurations we actually get.
I just don't understand
Yeah.
is how do you know that you're halfway?
Oh, I haven't talked about how we're going to do this. I'm just trying to motivate it a little bit. I'm trying to say that if we figure out a way to store halfway points, then we're there. So now let's try to go through the vague door that's opening for us and see if we can, blow away the mist and make it work. But we got to have a sense of where we're headed instead of just kind of flailing around. So before I actually write the algorithm down, I'm thinking maybe I can come up with another way of thinking about this that might be clearer for you. Okay, I got a way. It's just the same thing, but maybe this will help you think about it. Let's say that somebody gives you a book, and in this book is a description of a big cave, and a description of the passages in the cave. And on page 1 is the entry passage, and that's called I0. And there's also a room at the end that has gold in it called I gold. That's the final configuration. And you're supposed to figure out whether there's a path from the entryway to the gold. Because this cave is complicated, and maybe there's a way to get there, and maybe there's not. Now what the book describes to you is you can turn to any page. Every page has a configuration on it with a list of other configurations that you can get to. So if you turn to the page with I0 on it, there'll be just a list of other pages in the book. I3, I8, I15, and you can go turn there and see that you can get there. Everyone understand so far? And then if you're on page I15, it'll tell you that you can get to page I26 and page I355. You have this book, and you've got to figure out a way if there's a way to get from I0 to I gold. And you've got a piece of paper in your hand, and you're not allowed to write down too many things. That's exactly what this problem is about, but now it's a little more concrete. Or maybe less so. I mean, it's really the same thing, but I think it might be easier to think of it this way. You got all the time in the world you want. You can thumb through the pages as often as you want. You can backtrack. You can look at them again and again. Go wild with the exponential time. That's okay, but you cannot write down too many things. Does that help a little? Maybe? Gary? Maybe? Yeah? All right. All right, well, here's our method. Any kind of simple method doesn't quite save you much time. I mean, if you start looking at I0 and seeing all the things it goes to and write them down on a list, and then seeing all the things those go to and write them down on a list, you just end up generating this tree, a path through the tree, and that's too many.
Is rewriting, does that violate the space?
If you erase, and then you can erase.
Okay.
And you reuse the space, absolutely.
So, and it's a tree, so there are no loops?
No loops.
Okay. So,
Well,
so once you move to the next room, you could erase what you had before and just write, oh, but then if you were wrong, you're wrong. Okay.
it's true. I mean, once you know you can get to here, there's no reason to remember all the things behind you.
So at any given time, you only need, but you won't have the path.
Well, we don't really need the path. We just need to know if you can get there.
Since it's a binary tree, doesn't forgetting everything above you essentially one step at a time correspond to finding the middle point? I mean, you're at the top. You go down to one of the next two, and then you forget the path. You forget the guy above, and you just focus on the tree that's below you now. That essentially is the middle point, then.
No, the middle point is actually, if this is, say, 100 from top to bottom, the middle point is the 50th spot.
Okay.
So it's actually the halfway point down there. It's not ruling out half the choices. It's getting halfway to your goal in that one computation. So you can't quite do that. All right. Let me write out this algorithm. It's a recursive algorithm that isn't too hard to understand. It's only 3 lines long, and it's surprising how short it is. But here it is, basically. We'll call it Savitch's algorithm. So the first thing he does is he tries whatever he's going to do for every single final configuration sequentially, one at a time. That doesn't matter because he can erase the tape in between each one. So the main idea is to show that he can do it from the initial to a given final configuration. But he's got to try all the final configurations to make sure he finds it if it's really there. So let's just put that in the beginning. For each final configuration, and you can generate all the final configurations just by taking the accept states, and connecting them with all possible tape symbols. I mean, you can just generate these final configurations. For each final configuration, IF, check if there's a path from I0 to IF using k steps. And k is initialized, I shouldn't say k, sorry. I'll just say the right thing. This many steps. Okay? See if there's any way to get from the beginning to a final in this many steps or less. That's the procedure that he's going to write. And he's going to run this procedure for every single final configuration. But that doesn't add any space because once he runs it once, he erases the tape when he's done, and then he just starts the tape again. So we only have to consider one of these runs as far as the space goes. The time is going to add, but we don't care about the time. All right, so how does he do this? How does he check if there's a path between here and here in this much time? Here's his algorithm. Path I, J, M steps. Here's his algorithm to figure out if there's a way to go from this configuration to this configuration in this many steps. And he does it in this binary way. He says, try everything. And we'll call everything L. Try every single L and see if the path from I to L can be reached in half that many steps, and the path from L to J can be reached in half that many steps. If you want to figure out if there's a path from configuration I to configuration j in this many steps. Try every single L there is in the whole world. Try them all. Try all q, k, s of n times s of n. Try them all and see if there's a path from I to L with m over 2 steps, and if there's a path from L to j with m over 2 steps. If any one of these L's work, you stop and say yes. If none of them work, you stop and say no. Okay, it's recursive. What's the base case? If there's one step in between them, you don't split them into two parts. So we'll put that in here. There needs to be a base case. If m equals 1, then if I can reach j, accept, else reject. So if there's only one step between them, check directly whether I can accept j, and then stop. So try every single L. If any of these are true, any of these true, then accept. Otherwise, reject. That's the idea. 3 lines. Let's analyze it, because now we go back to analysis of algorithms. Let's analyze the space for this algorithm, because it doesn't take a lot of space. It's surprising. Let me stop before I analyze the space and make sure everybody knows what it's doing. You all know how to analyze time probably better than space. Maybe we should analyze the time first, because the time isn't s squared. The time's bad. How do you analyze the time for this? To do this problem requires 2 problems, each of which is half the size. And you see this loop? How many of these half-size problems do you have to do? A lot. A real lot. Look at this. It's ridiculous. How many things are there? Here are the number of configurations again. Let's just make it simple for a moment. 2 to the s of n, more or less the number of configurations. So what this says is, if you want to figure out this problem for s of n, if somebody gives you s of n, you're going to do 2 problems, each of which is half the size. And then you're going to do that how many times? 2 to the s of n times. And then it takes one statement to maybe do the if, to check on the if statement. So look at this. This is horrible. This is clearly exponential. I mean, the recursive relationship itself has an exponential bound in it. So the time is terrible.
The m is odd. You can't split it in half.
Yeah, so we split it as close as possible to half. That's not going to matter. Just do n over 2 ceiling. It's not going to. Just round up. That won't be a problem. All right, so the time here is bad. And part of what makes Savitch's theorem so elusive is that you're so used to trying to save time that you don't think of algorithms that happen to save space if the time is really bad. You don't think of doing this because you can see it's just ridiculous time-wise. But space-wise, it's really good. And you should develop an intuition to save space, because it's really kind of a cool thing how much space this saves. So let's try to figure out what this thing actually does. It starts, and it has this stored in memory and this stored in memory. And then it tries its first L, a recursive call. It tries something out here. And it checks recursively whether there is a path from here to here of size m over 2 and a path from here to here of size m over 2. Right? Now let's go through it recursively. Let's say none of these are path 1 yet. So now it has to do, what does it do recursively? Right, it does this first half recursively, right? So it checks if there's a spot between here and here, halfway. And then it checks if there's a spot between here and here. And finally, it checks if there's a spot between here and here. And let's say these distances are 1, and it succeeds. So this is a success. I'll make the line, success. What does it do now? It recursively continues and does this second half. So it tries something in the middle here, and something maybe in between those two, and then it gets finally down to sizes of size 1, and it checks this, and that's OK. And now where was it up to? It was up to this second half, right? And it does that. What does it actually have stored right now?
Throw away that.
All these things that I checked, it can throw away. In fact, they are thrown away. They're off the stack. Bye-bye. The only thing that's remaining on the stack right now, when it goes back to do this and this, is this guy and this guy from the first call, and this one from the second call of the second recursion. And now it goes down again deeply, and deeply again. And sooner or later, it checks this off, and it knows I finished my first recursive call. There is really a way to get from here to here in half the place. And then it no longer needs this or any of these, and it goes back to just storing two things. The point is, what it really ends up doing at any point storage-wise is storing a configuration for every halfway spot in between. And when it finally finishes that one little section that it's doing, it pops back up, erases those things, and goes down to another section. And the maximum number of configurations on the stack at any time is the number of configurations it takes to have this over and over again until you're down to a configuration difference of 1. And that's exactly the log of the distance from here to here. And that gives you something more or less S of n. Right? So that's the analysis of the space of this. The analysis of this space actually has nothing to do with complexity theory. It's just an algorithms problem. And it's understanding recursion in stacks. This is really a good question for what's going on in scheme if you did this algorithm, that the stack doesn't overflow. That it's the time that would slow this down, but the stack would never overflow until you ran out of memory. All right, I'm kind of relying in this last step a little on your intuition about how recursion works and how stacks work. So if you're a little weak on that, you're going to have some trouble understanding what I just said a few minutes ago with this idea. But let me stop. Maybe I can explain it in a different way. Let me answer questions first. Yeah, Doug?
I'm just remembering there were times doing recursion where we would have a stack overflow error, and trying to kind of compare with why is this one specifically not overflowing? It seems that
this doesn't overflow because you're cutting down this parameter by half every time.
Right.
So the stack, how many active procedures does the stack ever have on its list at any time? It's got the original. It's got this one. It's got another half, and then it's got one. And when it succeeds in that one, it pops it off and puts a new one on. And when it succeeds in that, it pops it off, puts a new one on. Sooner or later, it'll get down to here. But then all the activations for this have been popped off already. So it never has both of these on the stack at the same time. It finishes with this one before it gets to this one. So the number of actual procedures that it has active in memory at any time that it has to remember to get back to is the number it takes to take m, have it down until it gets to 1, which is the log base 2 of m. Does that make sense?
Yeah.
Michael? Here.
If the time is so awful here, why doesn't it move up to the exponential time ring? Why does it get to stay in p-space?
Michael asked a good question that really does merit a good answer. Let's see if I can give you one. I just showed you that if you have an algorithm in NP space, that I could simulate it and keep it in P space. So that NP space, even though it contains P space, actually equals P space. And you notice that this simulation actually takes exponential time. So everything you notice is true. I also just showed you that if you have something in NP space, I'll write it out here. This is a little bit of an unfair picture. Here's NP space. This is our first picture before I showed you that P space can simulate NP space. NP space is certainly bigger than P space because it's P space with non-determinism. Right? So it's certainly at least outside. And I just showed you that it was equal because P space can simulate it. And you're asking me, well, isn't it true that exponential time can also simulate it? And the answer is yes, it can. NP space is certainly inside exponential time. And I didn't mention that, but it's true in our discussion that exponential time sits outside these two. So that's all it really says. That's not as clear as the answer I gave you, maybe, huh? I don't know. Now you're confused. I guess the answer to your question is that there's no issue there. What you said is right. It's true that exponential time can simulate non-deterministic space. Yeah. What?
We know that exponential time is bigger than polynomial time, but we don't know that p space is bigger than polynomial time, right? So we don't actually know that this is exponential, given that.
We don't know that this has to be exponential.
Right.
We don't know that. I know that I can simulate NP space with exponential time, that NP space is contained inside exponential time, that I'll never need worse than exponential time to do it. But for all I know, there might be a faster way to simulate NP space. I might be able to simulate NP space in polynomial time if I was really clever. I just don't see a way to do it. In other words, P space, it looks like this, but for all I know, these two categories are not only the same, but they're really the same as this. But that we don't know is true, and we think it's not true. This isn't answering your question. So maybe ask your question again, and maybe I can...
I think Neil's right. The rings.
The rings are bad.
So, I guess what I want to say is,
Yeah?
well, if just this algorithm, maybe there's another one. Who cares? We have this algorithm which we know is exponential time.
Absolutely, right.
So
that shows that there's that if you give me a non-deterministic p-space algorithm, that I can come up with an exponential time deterministic one that does the same thing. And because of that, I enclose the whole category of NP space inside exponential time. That's my justification for writing exponential time outside the ring here. That's all.
I sort of want to push things out, but that's not really what those rings are saying. The rings are saying everything's enclosed.
The rings are saying that these are enclosures. We don't know if they're proper enclosures. We know that there is a difference between P and XP time. We know that. But we don't know if there's any difference between P space and P. Those might be the same. We don't know if there's a difference between NP and P. Those might be the same. You can't push it out just because the way we tried ends up making it exponential time. There might be a better way to simulate this with time. Still confused now, right?
Oh, it's a little better.
A little better, OK.
We were talking about if you could put space and time requirements on the particular rings.
Oh, that's another question. And maybe that's kind of what you're getting at intuitively. And maybe it would be nice to have a class where we say it's polynomial space and it's this amount of time, simultaneous. And people have done that. And there's a lot of literature about that. And there's even complete problems for classes like that, simultaneous space and time. But that makes the picture more complicated, and it's kind of not really at a first course level. So we're not really talking about any of those things.
We need to do it in 3 dimensions and color.
Oh, yeah. Good color. Sharon, yeah.
Is what you're saying that if we could prove that when we make this change to determinism, we had to do it in exponential time, then that would sit in the exponential time?
If we prove that doing this simulation actually required exponential time, I don't know how we could prove that. But if we could prove that, then we would know that P space is definitely not polynomial time. We know that these two things, the border here is a real border, and that these two can't collapse together. But we don't know that. For all we know, this, and this are all the same collapsed circle. I know they're contained in exponential time, but if I could show you for sure that you really needed exponential time, then it would spread these back out. There's still the possibility that P is powerful enough to simulate NP space. How about this? Here's our hypothetical categorization. I've convinced you that XP time can do NP space, and NP space can do P space, and P space can do P. This is enclosures because space is always more powerful than time. Space is the number of cells you visit. Time is how many steps you take. So anything that has a number of cells visited, that has a time that takes n steps, certainly has to take at least n cells. This is because it's non-deterministic and this is deterministic. So this is more general than this. And this is because if you have something non-deterministic polynomial space, there's only so many configurations you can have. And if you just run them all through, you get exponential time. So the question is, are any of these collapsible? And I just showed you that if you give me anything here, I can simulate it here. So that collapses these two. This line just goes away. Those two are the same. I also showed you that you give me something in here, I can simulate it there. But big deal. That's what I knew already. It would be nice if I could show you that I could take anything in here and simulate it here. That would collapse those two. And that's kind of what Michael's asking about. He says, well, you showed me that this takes exponential time, and that just leaves the picture the way it is. If I could prove to you that I couldn't do it in anything better, then it would show that this border will never collapse. If I could prove to you that that simulation has to take xp time, then it affects this border, and it shows that this border is... In fact, if you could do it, it's a huge result. Showing that polynomial time is different than polynomial space is the next most open question after p versus np. It's not quite as strong as showing p is different than np, but it's pretty darn good. Yeah. Okay, shall we move on to topic 2? Any more questions on this one?
I'm still trying to kind of understand how the algorithm itself is going to work. I guess the piece that's confusing me is that we now have, we've taken this this exponential expansion tree of all the possible configurations of our finite state machine, and we're now sort of treating it as a graph and as paths through the graph. I'm just not quite sure.
It's a tree, actually, yeah, but yeah.
Yeah, I'm just not quite sure exactly how we're kind of keeping track of, sort of which of these paths we've tried and which don't need to be tried again. If we're not taking exponential space to store every configuration,
you don't store hardly any of it. You store hardly any of this tree. All you do is use the ability to construct pieces of the tree very, very often. You do that an exponential number of times, but you don't actually store the tree explicitly anywhere. You don't even store a path from the top to bottom explicitly anywhere at any given time.
Right. But when we're going through this L, try everything L. That's definitely an exponential number of things.
Right.
If we were to write it all out, it would be exponential. So my question is, without writing is there a sequence somehow to all this L, so we just kind of know?
You can order it any way you want. Well, you're gonna generate them all, so you could generate them all in some kind of a reasonable order. The tape symbols, the state starts in the first tape symbol, all the other possible tape symbols in lexicographic order. The state moves over to the next, the head moves over to the next spot, all the tapes in lexicographic order. You can certainly generate this out in some systematic order and remember where you were up to. It's the control of your program that remembers where you were up to, is the real answer to your question. And the control of your program is very, very crucial. It remembers that you tried these and you didn't try the others, and at any point it only stores one of these L's and a stack full of all the others until you get to the base case. So as far as the configuration it actually remembers at any time, it's the initial, the final, and a stack of other configurations equal to the number it takes to have the distance between the original and the final repeatedly until you're down to one step. So yeah, you hardly look at the thing at all. And you could really do this. Like if you were in that cave and you had this book, you could really do this if you had a lot of time. You start on the first page, you're trying to get to the gold on the last page, and you know that there's presumably 80 steps in between.
Right.
So you say, I'm just going to try all the pages and see if there's a way to get from this page to this page in 40, and from this page to this page in 40. And now you remember that middle page. Put it aside somewhere. You write it on a separate piece of paper. I'm on page 32. That's the page I think. And now you say, okay, well, I got to do this recursively. So the second part I'll do later. And right now I'll just concentrate on the first part. I got to pick another halfway spot. Say that's on page 6. Another halfway spot, that's on page 4. And now I'm down to things of size 1. So I can get rid of 4 because I know there's a way to get from 1 to 6. And now I work between page 6 and 32. So you really are not storing too many configurations, and you just remember how much you've done. I guess your question is, how do you know how much of the path you've done? It's because this control keeps track of that.
Well, it's also just sort of where is that book stored? Because the place where your little metaphor doesn't quite hold is that if you have the book,
yeah,
then you've taken sort of exponential space to write your book out. Right.
Right. You don't really have the book. What you have is
you're kind of figuring out the pages as you go. It's sort of like you're going back through the book.
What you really have, that's right. What you really have is a description that tells you, you don't really have a book. Right. You've got a machine. And you can type in a page of this hypothetical book, and it'll tell you what's on that page. That's what you really have. And you're allowed to write down a few pages of where you were. Yes, that's a better metaphor.
So we probably have a Turing machine that has, maybe several small tapes or something like that. There's little areas in the tape where we're keeping track of a few key things.
Right.
That allows
Right. But most of what you use is the ability to generate.
Bounded.
It's bounded by very little. Yeah, by s squared of n. So there's s of n configurations that you need to keep track of on the stack. Each one of the configurations takes s of n space. That's s squared of n. That's Savitch's theorem. Yeah, that's a good point you brought up about the metaphor. You don't really have this book you're looking at. You have the ability to, you have a machine that lets you know what's in the book. You give the machine a page, it tells you what's on that page. That's a much better way. It's a Pokédex, as my kids play with. None of you know about Pokemon. You're adults. Why would you know? Unless you're that weird big fat guy in The Simpsons who owns a comic book store. Then you'd know about it. Whoa. Since I've done that, yeah. All right, second topic today. Okay, let's think about this for a minute. Let's consider Turing machines that work in a certain amount of space. Let's say linear space. Okay, they never use more than linear space. Guaranteed. And I want to know something about this set. The set of all Turing machines that accept themselves, but these are Turing machines that are linear space bounded. They're guaranteed never to use more than linear space. Everyone understand the difference between these and general Turing machines? General Turing machines can do anything they want, run amok on the tape, and these Turing machines are guaranteed that they never use more than linear space on the tape. So here's the input on one tape. They use another tape that never use more than the length of their input. And I want to know, can you decide this set? Can you decide, given a Turing machine like this, whether it will accept itself, yes or no? Guaranteed that this machine never uses more than s of n symbols. So do you think this is decidable or undecidable? Can you write a program that decides this?
Is n the number of states of the Turing machine?
N is the size of the input. This is a Turing machine that takes an input and never uses more space than the size of its input. So in the case of accepting itself, n would be the size of the Turing machine.
Does the machine have to conform to this as well?
No, it doesn't. The machine can, right. Right, Jeff asked a super question. Does the machine that does this have to be a member, have to live in the city? Right? That's the next half of what I'm going to talk about. If I asked you whether there was a way to do this with a machine that lived in this town, the answer would be no. How many steps this one is taking. And if this thing ever takes more than this many steps and doesn't say yes, then it stops the simulation and says, I know this machine will never ever accept. Because it's supposed to accept within this much space. It's supposed to accept without using any more. And it's already used enough steps to fill this tape in every single possible way it possibly could. So from now on, it's in some loop. And if it hasn't accepted up till now, it won't accept after now. It cuts out the infinite possibility into a finite category. And it's the same idea that we've done 3 or 4 times already in different ways. The ability that if you have a space bound on something, it implies a time bound. And if you have a time bound, then after that time bound is over, you know if it hasn't accepted yet, there is an infinite loop and it will never accept. So a general Turing machine can decide this set. This is decidable. Okay, this is the kind of question you could get on a problem set, and the answer would be this is recursive, this set. It's more than recursively enumerable. You could actually decide this yes or no. The yes part's easy, you just simulate. The no part's a little harder. You count up to here, and when you get past this number, if the answer hasn't been yes, then the answer's no.
Wouldn't it be possible to break through the space bound before getting to that, though, if that's all you did is just fill up your space?
I'm not sure I understand, Chris. Ask me again.
If something takes this long, then it's guaranteed to have and continues, it's guaranteed to have used more than its allotted space.
If something took this long, if it took this much amount of time, say we're simulating this machine, it took this much amount of time and it hasn't accepted yet.
Right.
Then I say stop and say it's never going to accept.
But
What's your question? Yeah.
You say it's never going to accept. It's either in a loop or it's not, or it's beyond n space, right?
Oh, the possibility that it's beyond n space will never happen. You're guaranteed that these machines do not use more than n symbols. That's given to you. These are S of n equal n bounded Turing machines, space n Turing machines.
So that's what you were checking for.
No, we don't know that. No, you're given.
You're eliminating the looping.
I'm eliminating, well, I guess we could check. I mean, you could give me a Turing machine that you claimed was, and then the second it goes past that space, I would stop and say, no, that's not even a legitimate Turing machine in my category. I could check it myself, but you might as well just assume that's true, because that's easy to check. But the key thing is, the hard part is if it doesn't go past that S of n space, and then you think you might be in an infinite loop, just check this amount of time, and after that you can stop checking. If it hasn't accepted, then the answer is no. Okay? So this is recursive. This is decidable.
So is it really true? Like,
Zoom in.
it's not glowing. It's a lie.
Glow in the dark chalk.
Maybe it'll glow tomorrow.
It doesn't glow.
It says glow in the dark, glow in the dark, glow in the dark.
It needs to be set in the sun for a while.
Your results may vary. All right, well, so put a black filter on the video and see what happens. Okay, so now here's the next question, and this question actually is at the heart of the space hierarchy theorem. And I don't want to get into too many technical details, but the basic idea is really straightforward, and you've seen it before in the many diagonalization examples we've done. The next question is, and it's what Jeff asked a minute ago, a really good question, is there a way to decide this set if we don't allow a general Turing machine? A different kind of decidability. Is there a Turing machine that is bounded with S of n equal n space that can make this decision? Is there a member of this group of Turing machines that's smart enough to be able to check whether all other Turing machines in its class accept themselves or not? Okay, and what do you think the answer is? The answer is no, but we know it's decidable. That means there's some other Turing machine that takes a bound of space that's bigger, because that's the only possibility for one that does work. There's none that, I'm going to show you that there's none in this class that actually take this amount of space that can do it. But I just explained to you that there's one that can do it. So that one has got to have to use more space. That means that there is a problem, namely this problem, the set of all Turing machines that accept themselves in a specific amount of space. That problem needs more space than S of n equal n. And then I can do it again from there. The set of all machines of S of n equal n squared will need something with extra space to recognize that, etc., etc., etc. You get a hierarchy of problems, each of which requires more space. And technically, you know how much you have to go up to make the thing work? You have to multiply this n by n to the epsilon, where epsilon is bigger than 0, and that's enough. Multiplying it by a log n, I think, is a little tricky. I'm not sure that quite works. There's some technicalities. So let me try to convince you that there's no S of n equal n space machine that will do this. So let's assume that there is. Let's assume that one of you come up with an S of n equal n machine that can decide yes or no, do all other S of n equal n machines accept themselves, only the ones that accept themselves, yes or no. It accepts the ones that accept themselves, doesn't accept the ones that don't accept themselves. Is there a machine that does that? So I'm going to convince you there isn't, and it's this diagonalization proof. Okay, I'm going to convince you, there is no S of n equals n space Tm that decides the above. let's call this, let's give it a name. We'll call it Q. All right, who knows how to do diagonalization? How do I show that there's no such Turing machine that will do this? What's the trick? This is that same Barber conundrum. Conundrum. We assume there is one.
Should be able to find out. Too.
If there's a machine that decides the things that accept themselves, then there's a machine that decides the things that don't accept themselves. This machine will say yes or no. So if it says no, then we can change the no to a yes and a yes to a no. So if there's a machine that decides the above, then the machine can tell us whether one of these things accepts itself or doesn't accept itself. So then I have this strange thing. I have a machine, a hypothetical one, that accepts all S of n bounded TMs. It accepts all S of n bounded TMs that do, this chalk is losing its value, that do not accept themselves. A hypothetical machine that does this would imply a machine that does this, a machine that accepts all S of n equal n bounded Turing machines that do not accept themselves. This is that Barber again. Let's consider this hypothetical machine that should exist if there was such a thing that accepted this. And I'm going to show you that this hypothetical machine can't exist by contradiction. Therefore, there is no possible S of n equal n bounded space machine that could decide this, because it implies the strange Barber that can't exist. How do we know this can't exist? Where's the problem? How do I find a contradiction in this description? Feed it to itself. I ask you the question, here's an S of n equal n bounded machine that accepts all S of n equal n bounded machines that do not accept themselves. So, does this machine accept itself? If it accepts itself, it's supposed to not accept itself. And if it doesn't accept itself, well, that's what it's supposed to do. It's supposed to accept all the things that don't accept themselves. So it can neither accept itself nor not accept itself. Therefore, it doesn't exist. It's a nonsensical definition. And if this can't exist, then the thing that implied it, namely that there is a possible S of n equal n space machine that decides this question, that can't exist either. And that implies my hypothesis. My hypothesis that I'm hoping, and now I know, there's no S of n equal n space machine that decides that question.
Why did we flip why did it become that do not accept themselves?
Because this is the one that gives you the contradiction. The ability to decide this question implies you can decide the complement, because all the yeses turn to nos and all the nos turn to yeses. And it's the complement of this set that's the one that doesn't exist. In other words, there is an S of n equal n bounded space Turing machine that will enumerate this set, that will tell you if the answer is yes when the answer is yes. It takes the machine and it simulates it using S of n space, and it keeps working and working, and if the machine sooner or later says yes, it will say yes. But if the answer is no, it can't check that because it doesn't have enough room to count that high. And this is kind of the proof of that. There's some technical details that I kind of left out here, but they're really minor. And the idea is really diagonalization again. And whenever you need to prove that there's separations in classes, diagonalization is always a way to do it. But it's the heavy big guns. And it fails between P and NP. There's no diagonalization between P and NP. And we don't have a lot of techniques for separating classes out outside of the heavy tool of diagonalization. And that's what people like Mike Sipser, who came to talk here, and people in his group, they are dying to come up with ways to leverage out and separate these classes that doesn't use the big heavy tool of diagonalization, because this is just the same idea over and over again, and it can only separate classes that are kind of far away from each other. It doesn't doesn't get fine-tuning between those classes. So that's why they look to circuits and other methods of defining computation in order to somehow separate these things out.
Is there something special about this, the machines that accept themselves problem that makes this work where you can apply a general Turing machine can analyze a bounded Turing machine and turn something that would normally be undecidable or recursively enumerable into something that is decidable? Or it seems like that would be the case with anything, like any of those categorizing Turing machines problems.
It's true.
Now we know when it loops. Basically.
Right, but just like any diagonalization, anytime you add a little power so that the higher level can understand the lower level, there's a question about that higher level that it can't figure out about itself. And you can add in a little more power.
But the same thing could apply to lots of other
Sure.
Turing machine analysis problems other than just those that accept themselves, right? I mean,
In fact, it does. Right. Oh, I see. Is the set of all S of n bounded Turing machines an empty language?
Right.
All those things. Right. You can apply Rice's theorem ideas to things like this. Sure. All right. So there's a time hierarchy theorem that's very much like this. What I want to do just to maybe to finish up today is talk maybe 5-10 minutes about alternation, give you some general sense about what those results are, where it fits in our big bullseye picture. And tomorrow/Friday, we have a couple more days. I'll try to set up a lecture about the recursion theorem, about programs that output themselves. And perhaps, maybe in recitation today, I'll have Dimitri do some reductions, which I think will help you with problem sets, and then go over other questions on the problem set. So just another 5 minutes here about alternation. P, NP, P space. Let's get a real piece of chocolate. Okay. All right. I mentioned this idea of an alternating Turing machine the other day, and I'm going to remind you what it is. An alternating Turing machine has two kinds of states. States that are OR states and states that are AND states. A non-deterministic Turing machine, all the states are OR states. That's the best way to understand an alternating Turing machine, is in terms of generalizing a non-deterministic Turing machine. A regular deterministic Turing machine, you have one choice out of every state given a symbol on the tape, given a state in the machine. A non-deterministic Turing machine can have many choices, but we interpret the acceptance of that as if it was an OR. If this one, or this one, or this one, or this one works out and accepts, then I accept. So every state in that non-deterministic machine is an OR state. You can define AND states, so that then when there are many choices out of that state, the acceptance idea is that they all have to end up going to accepting configurations before you accept. And if they go to OR states, then there just has to be one of those computations from there that has to work. And if that goes to an AND state, all the arrows out have to end up in accepting configurations. So it's more complicated to decide whether you accept something or not, but your machine is kind of really powerful. And it gives you this alternating quantification that lets you write algorithms very, very quickly. And as I mentioned once before, there are many times where you can think of an alternating algorithm that solves a problem right away, even though the polynomial time algorithm is a little bit elusive. For example, there was a problem that I worked on a long, long time ago that there's an n to the 5th polynomial time algorithm for it, and you just don't think of it, given the problem straight up, even though the alternating idea is readily apparent. And it's an algorithm about figuring out how to take different graphs and put them on top of trees so as to minimize certain distances of the edges that are spread out in the trees. It's called an embedding problem. And it's an alternating thing because you spread out over the trees for every there exists, for every there exists, without getting into details. There are problems like that. So alternation is kind of a nice idea to think about. What's even nicer about it theoretically is that these alternating classes fit in with the diagrams we have here. And I gave this to you last time. I'm going to tell you again. Polynomial time turns out to be the same as alternating space log n. That means you have an alternating Turing machine that uses log n space. That's the same as a polynomial time algorithm. Polynomial space is a time polynomial. If you have an alternating machine and you let it run in polynomial time, that is exactly the same as the things you can do in polynomial space. So this is interesting. Think about polynomial time being here, and this saying, I'm adding alternation to polynomial time. When you add alternation, when you add non-determinism to polynomial time, it pops you up here. That's adding there exists. When you add universal, when you make it alternating, it pops you up the next level. Precisely. That's a very beautiful result. Add one quantifier, you're here. Add two quantifiers, you're here. Questions? All right. This is also a nice result, but it goes in the other way. Take space. Remember d space log n that was inside here, the most inner circle in the smaller picture before? Take d space log n and take it out of deterministic Turing machine land and turn it into alternating Turing machine land, and it bumps you up 2 levels to polynomial time. It's completely a dual situation. Add things to the space, and it bumps you up 2 levels. Add things to the time, and it bumps you up 2 levels. It's a really nice result that these classes completely coincide. No strange overlaps, just completely coincide. What about this, way up here? What if you have exponential time? What is that going to be equal to? A space of what? What do you think? Let's take a guess. Well, I need a function here, not a complexity class, right? So here, when I added log n to my A space, I got polynomial time. So if I add 2 to the log n, I would get 2 to the polynomial time, hopefully. So that's what happens. Polynomial space with alternation gives you exponential time. This is really the same idea as this. It's just lifted up at a higher level. These two are the same. But this is very, very nice. Now, the proofs of these things are not terrible, but they're also not simple. I mean, they really need a whole class or class and a half. Mike Sipser's book has these proofs. He splits it into 3 or 4 lemmas each. But the idea intuitively, and I'll just give you a 2-minute overview of this proof, because it's really not so bad. The idea is that you need to figure out how to simulate alternating machines that use log n space in polynomial time. So somebody gives you an alternating machine, and you got to simulate it somehow. So here's the alternating machine. It looks like this. Here's the computation. If it was a non-deterministic machine, you just have to find out if there's a path from here to here. But if it's an alternating machine, you have to find a subtree. A single branch on the existential and all the branches on the universal. A single branch on the existential, all the branches on the universal. You have to find a subtree of this tree that ends up ending with leaves that are all configurations. And the question is, how long does it take to find a subtree of a given tree if every one of these nodes takes at most log n space? And if you do the brute force run through the tree, you don't get polynomial time. But it turns out you can turn this tree into a graph called an and/or graph, and traversing that and/or graph is like working through directed acyclic graphs and finding a topological order and working your way back, computing the ands and ors, and when you're all done, it ends up taking only polynomial time. All right, that's a 45-second version of what really needs an hour to completely understand. But at least vaguely you get an idea that it's a simulation whose first attempt doesn't work, but if you collapse the data structure in a clever way and go back to some stuff in algorithms, you can make it work in polynomial time. And all these simulations end up being things that go back to graph theory and algorithms. They don't lie so much in the weird world of like infinity, what Dimitri talked about yesterday. They lie in the world of practical, can you figure out how to simulate one data structure more efficiently with another? So this stuff is not always just pure mathematics. It comes back to stuff that relates to programming, even in this back way. All right, so I want you to know these results because they're really cool and it's really beautiful and you should see them. We won't have enough time to talk about this in any more detail, I don't think, because there's other things that are better. But if we took a vote, you want to do more details about alternation or do self-reference recursion theorem. You want to do the recursion theorem? That's the consensus? All right. I can do more things like this next week during the Unix review week. If people want, we'll see. But otherwise, I'll plan to do a recursion theorem lecture tomorrow. The exam, as you know, is Friday. And unlike the first exam, I want this exam to be done here before you run off on vacation for many reasons, but not the least of which is I want to take them all with me and grade them over the weekend and have your grades done by when I come back. But also, I don't want some people have plans, some people aren't going to do it over the weekend. I want to have it relatively uniform. So I'll give you the time you need, but I'm going to collect them at about 3 p.m. and then leave.
When are we going to start?
I haven't decided, but I'm not sure if I'm going to do any lecture that day or not. But probably you'll have at least 3 hours to do it. So come early. Come at 9:30 because I might just start at 9:30. I want to see how much we get done in recitation today and lecture today and tomorrow, and we'll see how far we go.